In this lesson, we'll solve some basic friction problems, and then in the next lesson, we'll follow up with more difficult ones. First, though, let's review how we actually solve these types of problems. The first step, of course, is to draw the free body diagram and to show the frictional forces as unknowns. You can make these forces go in any direction you want, but don't assume that these friction forces are equal to mu sub Sn, their maximum value. Next, if we're going to use the friction equation, you have to be sure that f of s acts in its correct direction on the free body diagram. And finally, apply the equations of equilibrium and the necessary number of frictional or conditional equations if tipping is a possibility. Now let's apply these concepts to solving some problems. As a first problem, let's consider a box which is resting on an inclined plane at a certain angle. And of course, if the angle is too steep, the box will slip. And here's a follow-up problem. Say you place this brick on this inclined board. Will it stay in place or will it slip down the plane? Let's analyze a problem like this. And to do so, we'll consider this 100-Newton crate. And it's resting on this 30-degree inclined plane, for which the coefficients of static and kinetic friction between the plane and the crate are given here. In order to solve the problem, let's first look at the equilibrium of the crate. And to study that, we first have to draw a free body diagram for the crate. On it, of course, we have our weight downward. That's 100 newtons. Then we also have the normal force acting on the crate. We'll call that N sub A. And the friction force. And which way does it go? It has to go upward, doesn't it, in order to prevent the crate from sliding downward. Finally, on our free body diagram, we should report the angle right in here. And that angle is 30 degrees. The reason, of course, is because if the plane were to drop down to the horizontal, close this angle to 30 degrees, this line would go to the vertical and close the same angle. Anyway, let's apply our equations of equilibrium now in the normal direction, positive this way, and then along the plane, positive upward. So first in the normal direction, or along the y-axis, we have N sub A minus 100 times the cosine of 30 degrees. This all equals 0, of course. And if you solve, you get the answer of 86.60. And this is in newtons. Now we'll sum along the x direction. Again, positive up the plane. So we have f sub A minus 100 times the sine of 30 degrees. And this equals 0. Solving here, we get the result. The force of friction, in order to keep the crate from slipping down the plane, has to be equal to 50 newtons. Is that possible? Well, the only way to figure it out is to find the maximum friction force that can be developed between the surfaces. Therefore, we'll apply our static friction equation. Here we have that maximum value being mu sub s, which is 0.3, times our calculated value for the normal force, 86.60. If you do the calculation, you get an answer of 26.0 newtons. And if you compare this value with the 50 newtons that we've already calculated, you see that the crate will slip because this is the maximum possible friction force and this is the required one. Consequently, with slipping occurring, our friction force has to be calculated from the kinetic coefficient of friction. So the answer to the problem will then simply be 0.2 times 86.60. And when you do this calculation, you get the answer of 17.3 newtons. So the crate cannot sit on the plane and stay there, rather it slips downward. All right, now let's consider this problem, where we have to determine the force P needed to cause impending motion of the 200 Newton block. To solve the problem, we'll first draw a free body diagram for the block. And on it we have, of course, the weight downward. That's 200 newtons. And at A we have the normal force upward, and the friction force, which acts to the left, in order to prevent the motion of the block, which wants to go to the right. And at B, the same thing. N sub B and F sub B. This completes our free body diagram, and now we can apply our equations of equilibrium. We'll begin by summing forces in the x direction. We do that, we have P minus Fa and minus Fb. And all this equals 0, of course. Now we'll sum in the y direction. N sub A plus N sub B minus 200, and it all equals 0. I'll take moments around point A to eliminate these two forces. If I do that, I have minus P times 3. I also have minus 200. The moment arm there is 2. And finally, we have plus N sub B times 4. all equals 0. Now, if you notice, we have 5 unknowns in these 3 equations, so we need 2 more equations to solve. Obviously, if motion is about to occur or is impending, then f of a is related to n sub a, and f of b is related to n sub b through the friction equation. And so we'll apply this 2 times. So let me write this out. F of a is equal to 0.3 times n sub a. And finally, f of b is equal to 0.3 n sub b. Now we have our 5 equations with our 5 unknowns. And one way to solve it is to realize that I can substitute fa and fb up into here with these terms. The 0.3 can be factored out, and we can write this equation in the following format. P is equal to 0.3 times Na plus Nb. Now we realize that this sum, Na plus Nb, is actually equal to 200, isn't it? So if I put 200 in here, then the solution for P is pretty straightforward. 0.3 times 200 gives us 60 newtons. Right now in this problem, we have to determine the largest force P that can be applied to this bar, which has a weight of 100 newtons, without causing it to move to the right. There's friction down at A, and the coefficient of static friction is given by this number. Over here, this wall is smooth, and so we don't have any friction up here. To solve the problem, of course, the first thing would be to draw our free body diagram. On it, we have not only the force P, but also the weight downward, that's 100 newtons. And of course, at A, we have a normal force going up, n sub A, and we have a friction force. Since the bar wants to be pushed to the right, the friction force has to go to the left. And finally, up at B, since we have a smooth wall, there's only a normal force acting here. First, we'll begin by summing forces in the y direction to find n sub A. Here we have n sub A minus 100 equaling 0. Solving for n sub A, we get 100 newtons. Now we realize that we do have friction here, and so therefore we can use the friction equation to find the force at A. Here we would write f of A is equal to 0.2 times 100. Of course, if you work this through, you get an answer of 20 newtons. Now that these 2 values are known down here, we can take moments around point B and get a direct solution for P. We have the following. P times 2, and then plus 100 times a moment arm of 1.5 minus 100 times 3 minus 20 times 4. Of course, all this equals 0. Solving for P in this equation, we get our result, 115 newtons, the maximum force that can be applied to the bar before it breaks loose from the surface down here and begins to move this way to the right. Well, here's our final problem. Consider this roll of tape, and someone's pulling upward on it, attempting to try to turn it. We'll assume the tape is up against a smooth surface here and on the rough floor down here. We'll try to analyze a problem like this to find the force required to cause the tape roll to turn. To do that, we'll consider this cylinder, which has a weight of 400 newtons. Here's a smooth surface, and of course, a rough surface. To solve this problem then, the first thing to do is to draw the free body diagram for the cylinder. On it we have the weight downward, which is 400 newtons. And we have the normal force of the surface down here on the cylinder, call it n sub A. We also have the friction force, which has to act to the right in order to prevent the clockwise motion of the cylinder caused by P, call this F sub A. And we have the normal force here, n sub B, force of the wall on the cylinder. Free body diagram is complete. Notice that we have 4 unknowns, 3 equations of equilibrium, and we use the friction equation down here because we have impending motion of our cylinder. First, we'll apply our equations of equilibrium. Summing forces in the x direction, we have f of A minus n sub B. And of course, all of this has to equal 0. Now we'll sum in the y direction. When we do that, we have n sub A. We have minus 400. And of course, plus P. And this all equals 0. We'll take moments around point A in order to eliminate the 2 forces down here, and also the weight, of course. We have n sub B times 0.5, and we have minus P times, again, 0.5. All this equals 0. And finally, we'll write our friction equation between NA and FA. And that, of course, gives us the following. F sub A is equal to 0.3 times NA. There we go. All the equations have been written, and now we have to solve these 4 equations for the unknowns, especially getting P. And how can we do that? Well, one thing we can do is we can say that f of A is equal to n sub B. And if that's true, then I can come here, I can cancel out my 0.5, and say that n sub B is equal to P, and therefore f of A is equal to P. Now I can substitute into here and write the following. 0.3 NA is also equal to P. And finally, I can solve for n sub A in terms of P, and I can put it up into here, can I? I'd have the following. P divided by 0.3 minus 400. And plus P, and this all equals 0. Now we can solve for P and get our result, 92.3 newtons. And so having completed this problem, now we'll end our lesson.